Okay, thanks everybody. For those that didn't see me yesterday, my name is Jeremy Howard. I'm a deep learning researcher and teacher at FastAI and associated with the University of San Francisco. And we're going to talk a bit more today about machine learning. So what is machine learning? Machine learning, very simply, is any type of algorithm where a computer can learn how to solve a problem to at least to some extent on its own, rather than being programmed. This is the 60th birthday this year of machine learning, so it's a very well-established and old area of computer science, and it's in fact 60 years since it was first successfully applied. 60 years ago, an IBM researcher called Arthur Samuels taught a computer how to play checkers by having it play against itself thousands of times. And within not very long, the computer had learnt to beat its own maker. So ever since then, there's been millions of pages written in academic journals about machine learning, and more recently, we've seen more and more impacts on our own lives from machine learning. Companies or organizations that ignore machine learning when it comes into their field do so at their peril. Many of you might remember this used to be the homepage of the internet. Something like 80% of people used this as their homepage. This is Yahoo. And I actually had a friend who was starting his own web portal, as they were called back then. And like everybody else, his approach was to borrow from the Yahoo theory. And the Yahoo theory was, let's have a room full of human experts. They called them editors. And editors would surf the web. And they would surf the web and find cool stuff. And then they would use their expertise as humans that understood other humans to categorize it into this vast taxonomy of which you see the top bit here on the Yahoo homepage. And that is how the web was organized. There were very few people in this industry who really cared that much when this company came along and replaced all of that with a single text box. I heard many people from Yahoo and their competitors talking about how this was going to go nowhere. Because behind this text box was not a room full of human experts who deeply understood humanity and what people wanted to read, but instead it was an algorithm. It was a machine learning algorithm called PageRank, which automatically surfed the web and automatically decided what it thought you might want to read based on your query. The intuition of all of those people who had spent years in this industry, we now know, was totally wrong. It turns out that the algorithm could do a better job. And we've seen this play out again and again over the last couple of decades. For example, Amazon. So many of the big booksellers told us when Amazon came along that an automatic recommendation system for books was never going to be remotely as useful as going down to your local bookseller and talking to a human who was an expert on the very human question of what kind of book might you like to read. Somebody who you could have a human discussion with about this is the kinds of books that I've liked and could you tell me what I might like to read next. And yet now we know this won the day. Most of the big booksellers are now either totally out of business or have dramatically reduced their size and profitability. The ability of machine learning to solve problems surprises even the companies that create them. In fact, just a few years ago, this was Google's April Fool's joke. It was called Autopilot. And the joke here, of course, was how ridiculous this is, which is that Google Autopilot said, yes, we now have made Gmail so powerful that it will answer your email for you. If you had a message from your therapist asking about your compulsive lying, then it would automatically build a response based on your prior experiences. So, of course, the real joke is that just a few years later, it was real. And now, if you go to Inbox by Gmail, it will actually read your email and suggest some possible responses for it. And this is actually a product. And last time I saw, this was being used for something like 20% of replies were just the automatically generated reply. And the rate at which I see my particular area of machine learning, deep learning, developing, the capabilities are often doubling about every month. So whatever you see in a product, you know that in research there's something far, far, far more powerful than that. So it's interesting that a company like Google can tell a joke about something that's funny because it's so ridiculous, and yet a few years later, that's actually something that they've released. It tells you how hard it is even for people deeply in that business to understand what's possible and what's not. So in medicine, we're starting to see a little bit of this happening for the first time. And interestingly, the successes are not necessarily coming out of the kind of big machine learning shops. We see some successes coming out of them, particularly Google with their diabetic retinopathy example. But this is a great example. This skin lesion detection, for one particular kind of skin lesion detection, the accuracy was improved by 400% by this algorithm. And this algorithm was developed by a group of people who are very much on the medical imaging side, not on the machine learning side. And all they did basically was to download one of the existing open source packages for image classification and throw their data at it to see what happened. And so we're getting to a point now where non-experts in the field can actually make significant progress using tools that they can download for free off the internet. It's certainly not at a point, I would say, where I would describe that as an easy thing to do, but as a thing which this example shows it can be done with great success. So one of the things that Rachel and I at FastAI have tried doing over the last 7 weeks is asking the question, how much can a non-machine learning person effectively apply modern machine learning techniques, and particularly deep learning? So we tried an experiment, which was we invited 100 coders, people with at least a year of coding experience, to join us at the University of San Francisco and spend 7 weeks learning about literally the cutting edge of deep learning. We just finished this experiment last week, actually. And I think the best thing I could say about that was I asked that group of 100 at the end, how many people are planning to come back for part 2 in February, and nearly every single person put their hand up. So nearly everybody, and in speaking to people, we heard so many stories of people saying that they had dramatically improved their business or their research. A lot of these people were neuroscientists, or they were people building space satellites, or they were people doing all kinds of different stuff, but they weren't machine learning experts per se. And every one of them that I spoke to told me that they had dramatically improved their ability to do their job by applying these kinds of techniques. We will hear from the other speakers some of the challenges involved in this. And I want to say, as somebody who's been applying deep learning for the last 25 years, that I've seen these challenges again and again. And I don't want to in any way underestimate them or tell you they're not there. But they're fixable, and they're well worth fixing. So for example, one of the first things I did 25 years ago was I showed a personal finance company that did car loans that if they used a computer to do their lending decisioning, who gets a loan and who doesn't, instead of their big room full of human loan auditors, that the computer would have done a better job. And suffice to say, that advice went nowhere, because all of the belief at that stage in the credit industry was that only humans can judge other humans and their ability to repay loans. You know, how could a computer possibly do that? And furthermore, how could we explain to a human why we rejected their loan if it had been done with a mathematical equation? And these are the kinds of things that I've heard again and again for the last 25 years, and in medicine I'm hearing again now. They're real problems. They're real challenges, but just remember that every industry, so medicine is pretty much the last industry I've seen to become a data-driven industry. And so remember that many, many other industries now have gone through this. The answers do exist. They're not easy, but they're well worth spending time looking into. And so I hope some of the other panelists today will tell us about what some of these challenges are and maybe talk a bit about some of the possible approaches we could take to getting over them.
Okay, thank you. So I'm Mei Wang. I'm professor of biomedical engineering at Georgia Tech at Emory. So yesterday I was talking about how to regulate our omic, especially genomic, for the precision medicine. So today I'm going to dive into talking about limitation. I actually think Rachel did an excellent job in already talking about the limitation of data mining right now. So what I want to do is dive into some more detail specifically related to biomedical AI. So the first thing is, why it doesn't work? Okay. Okay, so first thing is, I think Anthony this morning mentioned an important AI pipeline. How do we come from raw data? We need to worry about the experimental design, the patient collection for training the AI model, and then the data quality to the metadata. How do you extract the meaningful features? How do you get to the knowledge level, doing the knowledge modeling, eventually coming to intelligence and action and taking? I'm actually taking a different spin of what he presented, talking about the top 4 care areas in the biomedical AI right now. So the first one is data integrity. I think everyone was talking about, from yesterday and today, talking about garbage in, garbage out. So this is one of the major issues right now. To be able to provide the best evidence in medicine and health, we need a cleaner data. And in terms of getting cleaner data, if you have like omic molecular data versus the EHR data versus the imaging data, the current difficulty in the data quality are totally different. That itself requires a lot of data mining and the AI. Second one is the data integration, which actually we're talking about the knowledge and the science right now are sitting in silos. When we try to integrate them together to take a better insight of the scientific discovery leading to personalized precision health. Either we're talking about using molecular integrated with the imaging diagnosis, or integrated with EHR, and now even integrated with personal health record. That itself demands a huge amount of AI, like research. There are a lot of limitations. And then the third area is population-based learning, based on knowledge, plus individualize the inference, like how physicians do in the clinical setting for personalized care. That itself currently is one of the most behind area. Because of these 3 hypes during the AI period, this has been left behind for many years. That's actually demand a lot of research. And last one is adaptive learning. When you're actually trying to do the real-time decision making for continuum care, you actually, right now, some of the AI can help you get there, some cannot. There's no way for me to cover everything, but I want to actually mention one important study we discussed. I'm using that as an example to show what's the limitation of AI. I cannot cover every one of them. I'm just showcase a few of them. Remember Rachel talk about this gender bias when you're doing the general big data analysis? I'm actually from Atlanta, so we actually also looking into the health disparity, right? And then we were doing that research. We run into this one study, very interesting study. Some of you probably know it. Oh, actually, I didn't realize I didn't hide this slide. I was trying to hide slide. But let me actually quickly go over this. When I'm talking about the limitation, I said there's all 4 data analytics area has a limitation. And then currently, if you summarize data access, data quality, black box algorithm validation, and the feature interpretation, those are the major ones. But let me actually run into this detailed study. So this is a study we did multiple years ago, where it's very interesting that, based on the large study, it's showing that the woman taking like a hormone replacement therapy turned to have a lower than average coronary heart disease. Based on the initial AI data mining algorithm, so then the conclusion was the HRT will protect against the CHD, right? But in reality, is that true or not? This leads to the discussion yesterday about what's the limitation of data mining. Should we trust the black box or not? I can tell you the truth is we cannot. This is a particular example is to show that the randomized double-blind controlled trial show that In fact, it's the opposite. HRT causes a small but statistically significant increase of CHD risk. So if we actually purely trust the AI result without doing a real trial and validation, we're actually going to lead to a completely wrong like a diagnosis for medical care. So that tells us why we have to be very careful. Can we trust the black box or not? I keep repeating, yes, I said yesterday, I repeat again. We cannot trust AI for itself. We have to have the human curation in the process. Not talking about how do we do that, what are the other limitations, right? So another limitation, talking about, I was mentioning about the causal inference. Right now, less than 2% the AI system in the computer-aided clinical like a decision support or workflow support system are related to a real causality, right? The cause effect. And more of them are still related to the correlation, which I already told you how difficult, how like dangerous it is. And then, if you start looking in the causality study, one of the limitations about our current causal model is we have so many assumptions, limitations in the fundamental mathematics model we have. We actually have to understand medicine better to be able to utilize those models. Simple example, for Bayes network, it can actually model the directed relations as causal relations. However, a lot of our medical diagnosis, like I'm using ontology as a simple example, it involves a cyclic relationship. That kind of a relationship you cannot easily model without a like simple Bayes network. You have to use a revision of that kind of network. However, the moment you use that network, you actually enter another challenge that's related to the computational cost. For example, you want to generate like a graph modeling that cycling relationship. When you're trying to model the physician's causal inference, that itself can take you it's an incomplete problem. And then another, I actually talk about this model, the example in Monday's workshop, talking about how do we capture the physician's knowledge. Simple example, it's reverse engineer. It's very hard. We have the whole slide's image being scanned 24 hours per slide by robot-controlled microscope. Physicians select the area, especially the pathologist decided whether it's a cancer area, or necrosis, or stroma area. We actually doing the quantification, reverse engineer, we end up finding 2,600 features, right? When we actually doing that, of course, we create a quantitativity and objectivity in the process. Unfortunately, however, when we're talking about the interpretation, only a handful of features are interpretable by pathologists because those are related to morphology, color, that's interpretable. So that tells us that right now, we not only need to understand the black box, like I said, Bayes like causal inference, what it works, what it doesn't work, but also fundamentally, ultimately, for like a clinical practice, we also have to really interpret the features. Some, for example, we're talking about molecular blood test, like molecular marker. You absolutely need the final feature of what they are, right? That's the omic topic I discussed yesterday. But if for imaging, even though we're not getting there in terms of getting the, understand every feature, but at least we have to get some feature that we can get a proof by the pathologist first to put a rubber stamp on trusting your AI. So those are the fundamental limitations of data mining. Deep learning algorithm, biomedical interpretation of features is even harder. I don't have time to cover this, but many of us know that you use deep learner, you have this gradient vanish problem, and when you do regularization, you change a lot of property of your deep learner. As a result of it, it's harder to interpret your features. So those are fundamental limitations when we apply AI to medicine. So with that, I'm going to summarize with this one slide. This is actually what I put on for my workshop. Which actually I'm going to answer it based on the 25 years working in this area. What is the biggest paradigm shift for machine learning in AI in biomedicine? The number one is we're moving from academic piloting to the translational in practice. And the second, what are the challenges, the major barriers? I would call it two important challenges. One challenge is how do we translate the human knowledge? This is actually is very difficult, and how do we capture the care provider experience? And then another challenge is related to policy. We're talking about the data access and data collection, and those are all related to policy. HIPAA policy as well as the standard for our system. What are the short-term, mid-term, and long-term objectives? I think the short-term, as I already pointed, we have to first prove AI is trustworthy by our care provider. The midterm is we actually utilize the AI to provide more insight discovery to our physician. They first trust you, they're going to willing to trust your new result. And the third one, I call it, we have to invent a new algorithm based on medicine and biology. We call it the biologic and medicine-inspired new algorithms. Last one, what are the top 3 areas and action items? I actually want to summarize, also it's very important. The action item, I think, is we actually need to first, for AI to progress, we need to make data accessible. And the second one is education. I think Steve and Ronan will talk about it. And the last action item, convergence. So we need to have this conference every year and even more. It takes a village to solve this problem. Thank you.
Good morning. Thanks for the opportunity. My name is Suresh. I'm a practicing pediatric emergency physician and the CIO at CMIO at Children's Hospital of Pittsburgh. A quick faculty checklist. Do I have expertise in machine learning? No. Am I an AI expert? No. Am I an authority in neural networks? No. Have I published in deep learning? No. Did I train at MIT or Stanford or Harvard? No. Do I work for Google or Watson Health? No, and I don't own a startup. Additionally, I'm not a radiologist or an intensivist or a cardiologist. So while you're wondering, how did I get up on the speaker panel, in addition to it being a friend of Anthony, I'd like to share a couple of machine learning projects my team and I have implemented at Children's Hospital of Pittsburgh. A little bit about us. We were the first children's hospital in the world to get the HIMSS Analytics Stage 7 EMR adoption model. We've been continually ranked in the top 10 children's hospital list by US News. We are a magnet hospital, which is the highest level of nursing excellence, and you can see some of our stats, operational stats on the left side of the screen. I like to show pictures of my hospital. We are also ranked as a top 20 most beautiful hospital in the world. We have done more transplants in kids than any other hospital in the world. We also have a pretty active telemedicine service. You see 2 of our cardiac intensivists in the picture there. They're sitting in Pittsburgh, and they're managing a pediatric ICU in Bucaramanga, Colombia, South America. They round on those patients every day. And as far as data, we have about 200 gigabytes of clinical data monthly. That does not include imaging or pathology data. And we're up to about 14, 15 terabytes of Cerner data now going back a few years. And we get about 16 million new results per month. Highlighting one of our machine learning projects, application of machine learning techniques to predict 30-day all-cause pediatric readmissions. A little shout out to my colleagues in biomedical informatics at Pitt. And this is under our umbrella of using quality improvement science to improve transitions and reduce readmissions. So a little bit of a background. This is a financial burden, as all of you know. There are some CMS penalties for select unplanned readmissions. There is a movement towards more public reporting of readmission data. The impact is felt more acutely in adult hospitals, but even in pediatrics, we've had some claims denials for one of the 2 encounters, either the original admission or the unplanned readmission. So there is a need to look at this more critically. So our objective, reading from the slide, was to develop a predictive model which will provide a dynamic probability of a 30-day all-cause readmission to providers at point of care at a large hospital when we have about 20,000 admissions annually. Key points on the slide, we looked at 30-day readmissions, not 7-day, and the information had to be integrated into our EMR at point of care for all providers. So we used DRGs and ICD lists. Our training data set, we did not want to plug and play other available models, so we looked at our patients for a 5-year period, developed an algorithm, and refined it using a validated or a test set for the next 2 years. So some numbers, we had close to 10,000 readmissions in the training data set, over 50,000 controls. For the test data set, which was for 2 years, used for refinement purposes, we had 4,000 cases or unplanned readmissions and over 20,000 controls. We have an area under the curve of 0.79, which I think is good, maybe not great. And we're also looking at some specific, in addition to all-cause readmissions, specific readmission predictors for seizures, asthma, and pneumonia. We call this project as SHARP, which stands for System for Hospital Adaptive Readmission Prediction and Management. And this is what the provider sees at point of care. So if I'm the discharging hospitalist, let's say, and the patient has been medically cleared to discharge, I can click on the readmission risk icon in our Cerner menu. This is not an intrusive alert, and this pops up. So if this indicates for that particular patient, based on that encounter, there is a 75% probability of readmission within 30 days, then the provider has a few choices, or the care team has a few choices. They can go back to the family, indicate that they're higher readmission risk, and ensure that their discharge prescriptions, antibiotics, seizure meds, et cetera, are filled. They can ensure that the primary care physician follow-up is set for 3 to 5 days from then, and the neurology follow-up is also set. They can assure the family that a home nurse will call them in 24 to 48 hours, what's the right number to call, et cetera. And less likely, they could also delay the medical clearance and discharge of the patient for a few hours. Hopefully that's not done frequently, to ensure that we minimize the chances of an unplanned readmit. Switching gears, another project which has been in place for about a year is what we call Condition E, and E stands for Early EMR-Based Recognition of Clinical Deterioration. So I won't go into too many details. This is the Pediatric Rothman Index. Sharif talked about it in his workshop on Monday. We co-developed this product with Michael Rothman and ParaHealth. So this gives off an electronic alert. You can see the time value of the predictive tool. It's a score from 0 to 100, lower the score, sicker the patient. This takes into account about 25 variables, vital signs, lab tests, and system reassessments by nurses. So there is definitely some machine learning involved there. And the number is relayed through our VoIP phones to doctors and nurses. We had a nice write-up in the Wall Street Journal earlier this year. So this is a screenshot from there. And we have very good access to trend data. Some early stats from this. This has a sensitivity of about 60%, specificity in the low 90s, positive predictive value of about 40%, negative predictive value of 96 to 98%, positive likelihood ratio of 15, and a negative likelihood ratio of 0.9. Switching gears to organizational commitment. This is key. Putting on my administrator's hat, we take pride in being a data-driven and a goal-driven organization. For this fiscal year, we have 25 goals for the entire hospital. Almost all of those are operational, and 5 of those 25 goals are under information technology. And goal number 2 of 5 is the SHARP project, which I just talked about. So what this forces me to do as a CIO is to keep the progress on task, give out weekly and monthly reports, and I meet quarterly with the local philanthropic organization, which is funding this project. One of my favorite slides, the value equation in healthcare. Value equals quality divided by cost. And you can further split quality into outcomes plus safety plus service. And under service, you have satisfaction plus access. Now, even if you're not a hospital administrator, I urge everyone in this room, clinicians, researchers, scientists, entrepreneurs, industry experts, to memorize and apply this equation. I think it's a working definition. If you're creating a product in the lab, you may not need to know this at the initial stages, but when it comes time for implementation, especially in a hospital, this is critical. When our current grant funding dries up, if I am not able to prove to my peers and bosses that there is no clear financial ROI or a measurable improvement in quality and throughput outcomes, which are all validated metrics, the hospital is not going to fund this project. We recently hired our first data scientist, who is a fresh graduate from the Pitt PhD program. This is copied from his CV. I don't know most of these words and terms. That's why we hired him, so he can do the legwork. And in Pittsburgh, we are also fortunate to have this opportunity called the Pittsburgh Health Data Alliance. It's a collaborative between 3 big successful organizations, Carnegie Mellon University, University of Pittsburgh, and University of Pittsburgh Medical Center. And they are funding projects which are primarily based on big data, predictive analytics, and advanced genomic analysis. Last year, they funded 6 projects, and the early seed funding was anywhere between $500,000 to $2 million. None of those 6 projects involved children, so we are confident that with the next cycle, we'll have a project from Children's Hospital get funding from them. We're also really fortunate to be a part of President Obama's Personalized Medicine Project. And as you know, the aim of this project is to enroll 1 million humans in the US over the next 4 to 5 years. And University of Pittsburgh is one of 5 or 6 sites in the country. And our aim is the university's aim is to enroll 155,000 of the 1 million. And my aim as the lead at Children's is to enroll somewhere between 20 to 40,000 children off the 150,000 that Pittsburgh is expected to enroll. So super excited about this. We won't start this, at least in Children's, till mid or late 2017. And you can imagine the data that goes into it. It's not just clinical and research data, but social determinants, genomic analysis, et cetera. So this will be a nice machine learning project, and I strongly believe that this will be truly transformative. I'd like to finish by quoting my hospital president, Chris Gessner. You have to sell problems, not solutions. When you go to the physicians, you have to engage them in creating the solution. You have to be genuine in asking for the solution. They will identify work processes. You have to do it with them, not to them. So to all the smart young folks here whom we've been meeting over the last couple of days who are experts or dabbling in AI and machine language, if you come to me with a solution, I'm tuned out. But if you come to me saying that, looks like you have a problem, let's work on this together, then you have my attention. My email is on the slide. I'll be happy to answer more questions later. Thank you.
Okay, thank you. My name is John Williams. I'm lead data scientist in the virtual PICU at Children's Hospital Los Angeles. And I'm going to share a perspective on machine learning and challenges in medicine from the point of view of a team of data scientists working closely with doctors. I'm going to focus on specific projects and goals that we have and the challenges that we've faced in developing those projects. But I think the challenges you'll see are generalized, and hopefully these projects will provide an illustration of some of these general challenges. Okay, so the VPICU's goal is to use data and algorithms to guide treatment of the current patient in the ICU. And we take a couple of approaches. First of all, finding similar patients means the algorithm can examine the data that you have available for the current patient, and then go back and retrieve records of patients who are similar to that patient and present those to the doctor. And then the doctor is able to analyze what might have differed between the therapies given to those patients and how that affected the outcomes for those patients. Our second approach goes farther than the first approach in the sense that the algorithm more directly predicts response to treatments given to the patient, and perhaps ultimately suggests a course of therapy for the patient. So those are the big goals, and I'll talk about some of the challenges that we face. And I'm going to get to some kind of deeper challenges, but let me start with a more basic problem, which is no matter what you choose to do, you need an algorithm that can operate on the kind of data you have. And the kind of data we have is kind of messy. So it's time series data, and some examples are shown here. First problem is that these are time series data, but they're irregularly sampled. And most machine learning algorithms expect some regularity in the format of the data that they're given. So in order to put this sort of data into a machine learning algorithm, you need to either manipulate the data into a form that the algorithm can handle, possibly losing information, or you need an algorithm that can more natively handle the format of the data. And the other problem is missing data down at the bottom here. So this variable is ventilator rate. It's only there in the health record for patients who are on a ventilator. So what do you do with a model that's looking to use ventilator rate as an input, but you don't have, the patient's not on a ventilator, you don't have the data. So I think that a good solution for both these challenges comes from deep learning. Recurrent neural networks are a deep learning model. And the basic structure is a feedback loop. So essentially, the model maintains a state vector inside this kernel here, which is updated every time a new piece of input comes in. And then at the next time step, it feeds that kernel's internal state back in and incorporates the next piece of information and gives you an updated output. It's nice in that it intrinsically handles the sequential data that we're dealing with. And so it has the advantage of being able to operate on irregularly sampled data and really natively understand the temporal dimension. I think in common with other deep learning algorithms, it can directly, it has the flexibility to directly model missingness of data. And this is something that was demonstrated in this paper by some collaborators of ours, which was published just this year. So I think we have a tool that's capable of handling this challenge. So let's get to a bigger problem, which is the difference between pure prediction and taking action. So data scientists like predictive models. We're really good at making predictive models in which you're given some labeled training data, and you learn a function that accurately predicts the labels of future cases. The problem is that you want to use the results of this model to inform how you intervene for the next patient. And the problem is that predictive models really can't account for intervention. Predictive models learn from a set of training data that are drawn from some distribution. When you go make an intervention, you're changing that data distribution. And that may invalidate some of the predictions that the models make. So I'll illustrate that, or a situation in which this arises. So this is from some work that David Leadbetter presented yesterday. So this is an RNN that was trained to predict ICU survival. And it can provide essentially real-time predictions. Every time a new piece of information comes in, it updates the probability of survival. And you see in this case, about 20 hours after ICU admission, some piece of information came in that caused the model to think that, well, this patient is really sick, it's not likely to survive, and the probability of survival plummeted. So what you like to do is use a model like this and say, okay, maybe I can vary this input and say maybe I can put in some counterfactual treatment and see how that would have changed the probability of survival. So how does some other intervention that we might have made affect the patient's survival? And that's what you'd like to do, but it turns out that the predicted responses sometimes come out wrong. So for example, we've looked at, say you can turn on or off some drug and see how that affects the probability of survival. And an interesting example was rocuronium. Rocuronium is a paralytic that is given to patients just before you insert a breathing tube. And it really shouldn't have any effect on the patient's intrinsic health. But what we find is that across the board, you give rocuronium to the patient virtually in this model, and the model believes that the probability of survival goes down. So that doesn't seem right. One possible explanation is that what's happening is that it's the information that the patient is being given, this paralytic, that the model is using to infer that, oh, hey, this patient's about to be intubated, this patient's sicker than I thought, so it's adjusting its probability of survival. So if that's the case, then really, I suppose the mistake is ours in interpreting that change in the probability of survival as a response to therapy. So I think that to really understand the effects of intervention, you need to use concepts that go beyond pure predictive modeling. And there are some approaches out there that we're looking at that I think aren't yet widely used in our field, but I think are definitely worth pursuing. Causal inference attempts to infer or estimate the effects of intervention from purely observational data, or at least tell you when you don't have the data required to make that inference. And reinforcement learning directly incorporates decision-making and intervention into the modeling process and aims to come up with optimal treatment strategies. So I've talked about, let me go back. So I've talked about the messy data and how we think we have tools that can handle the messy data. I've talked about the difference between prediction and intervention, and there seem to be promising methods that are worth pursuing. But let me get to the third and last challenge, which is that the data in the EHR are essentially interpreted. They've gone through some human interpreter, who is the nurse charting the data. So you can think of the EHR as a tool for communication between caregivers. And so that means that what's recorded, the numeric values that are recorded, the frequency with which things are recorded, the notes, reflect the nurse's judgments as to what is important to convey to the rest of the care team. And so it's really not raw data, it's really not some just downsampled reflection of reality, it's some interpretation of what's important. And that's something that's a little bit hard, I think, for scientists to get their heads around, or maybe it's something that we're just not familiar with. Let me give you an illustration, and hopefully this is visible to you. This is a series of heart rate data over a period of about a day and a half. The circles are what the nurse charted, and these little crosses in between are some high-frequency monitor data, which we happen to have for this case. And so what you can see is that at a kind of high level, the charted values pretty much follow the monitor values, so that's good. There's no gross disagreement. But let's zoom in on this period of 8 hours. So a couple interesting features here. One is that there was a really sharp drop in the heart rate, and that was indeed captured. The nurse noted that. That seemed important. But also, just before that drop, there was a peak that was not charted. Over here is another peak that was not charted at all. Why did that happen? Why did the nurse essentially omit to include this event in the chart? Well, it may be that essentially the nurse felt that was irrelevant. Maybe the patient was being suctioned. Maybe the patient rolled over at that point. There was a temporary change in the heart rate. That didn't really seem medically relevant to the care of the patient. And so that was just left out of the chart data. So we don't really know why, and we don't really know. I think one of our challenges is figuring out how that might affect our modeling. But what we do believe is that the best way to get a handle on this clinical reality is by embedding ourselves with the care team. So here's a picture from morning rounds, and you see the usual team, but also embedded with that team, you see the data science team. And we think that's a vital activity for understanding the clinical reality. So I'd like to close by talking, by kind of, I guess, backing up a point that Suresh made. There's been a lot of talk at this conference, or I've heard some talk about what do clinicians really want? Do they want decision support? Do you want streamlined workflows? I think it's important to listen to what clinicians say they want, but it's also important to get in there and observe where the pain points are, where the difficulties, where the uncertainties are in the decision-making process, and see what are the problems that we can actually help with. So I'll close with this quote. Steve Blank is an author and entrepreneur who laid some of the groundwork for the method, the lean startup methodology. And he wrote, our job was to find a synthesis between our vision and what customers would accept. It wasn't to capitulate to what customers thought they wanted, or to tell customers what they ought to want. So I'll close with that.
Thank you, John. I'm Michael Fahey, Associate Dean at Schmidt College of Science and Technology at Chapman University. And we have a computational data science program there. I'm also organizer of a meetup group called the Future Chief Data Scientists in Orange County, and some of our future chief data scientists are among you today. I really appreciated Suresh's slide because that stuff applies to me too. I'm here primarily because I'm a friend of Anthony, and Anthony led me to believe that this audience was not as sophisticated as it turns out to be. So my presentation is kind of at a more elementary level of what an ELI 5 or explain like I'm 5 level of what are the limitations of machine learning in medicine. So artificial intelligence is the attempt to create machines that think like people do. And one of the things that people do is learn. Where do I point this to make it work? So we can think of machine learning as the ability of a system to improve its performance of a task based on experience and data. And I'm going to go through some of the basic things that go wrong or can go wrong or can limit performance. And in looking at this, it really seems to me that there's nothing, most of what I say is not really specific to machine learning. It's really things that can go wrong in any scientific endeavor. So just kind of quickly, I'll go through these things in more detail. Representativeness of samples, similar inputs with different outputs, noise in the data, we've heard a lot about that, overfitting of models, and dimensionality, also known as the curse of dimensionality. So representatives of samples. The main, I guess, classical approach of machine learning is classification. You want to look at your patients and decide which ones are going to be candidates for readmission in 30 days. And you create a model and you group them into different groups. And you might find that a test subject, that black dot, doesn't really fit into either of those groups. And we can say that we don't have enough data. The model fails to generalize because we have insufficient data. Now, some of our studies in traditional RCTs suffer from this. There was a study in the British Journal of Medicine that says 71% of randomized controlled trials don't use representative data. But Kevin Hall said yesterday the whole notion of representative data is wrong, that even identical twins have different phenotypes. And so the idea of having representative data is inherently a problem. Next, similar inputs with different outputs. You can have different diseases that exhibit the same symptoms. And so what your data looks like is there's no way to classify them appropriately. University of Maryland, for you data scientists, has a nice website that shows symptoms that belong to multiple diseases. And so you need to get lots more data to be able to distinguish situations like this. Noise, garbage in, garbage out. We've heard a lot about that. Recorded example outputs are not what they should be. So you can see that we have some blue dots down there among the pink dots that really shouldn't be there. And why can that be? Well, we've heard a lot of examples of that. You can have bias among the people that are encoding the data. You can have mistakes made by the experts. You can have measurement error. So there are lots of different reasons that can cause noise. There could be missing data. There can be, well, we've heard a lot more detail over the last few days about that than I can provide. Next up, overfitting. So this is, again, a classical problem where if your model has too many variables in it, you can fit the test data very precisely, but the closer you fit the test data, the worse your model becomes for predicting anything useful. So here's kind of a classic example of a situation where you have an upward trend and your simple linear regression model kind of shows you that upward trend. You can use a polynomial model and it will fit your data exactly, which you would think is kind of awesome, but that polynomial is not going to be very useful in predicting anything. So maybe this is a bit counterintuitive. If your model does too good of a job of fitting your data, it becomes less useful in predicting something. This is more of a machine learning, bigger data kind of thing where you can kind of classify into two groups with that simple curve, but if you have a more complicated curve that more exactly separates the blue dots and the orange dots, it becomes less useful as a predictive model. So the more variables you have in your model, the more closely you can fit your test data, but that doesn't mean it becomes useful. And there's a quote from John von Neumann, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. But having more parameters to fit your data more closely isn't necessarily a good thing. Finally, we have dimensionality. This refers to the number of different features or variables that we measure. And again, it seems like counterintuitive because you would think that the more variables you have that you track, the better job you can do of classifying your data and predicting outcomes. Well, so when I walk into Kaiser, they always put me on a scale, they record my weight, and they take my temperature. And so they have these X and Y values that you can imagine sitting in a two-dimensional plane. But then I go into an examining room and they'll take my blood pressure. So if we add my average blood pressure as a third coordinate, the same set of data that first existed in a plane now gets spread out in a three-dimensional volume. And that the data just becomes that much more sparse when it exists in 3 dimensions rather than 2 dimensions. And a lot of the Rothman score involves 50 different things that get tracked. We've seen situations in ICUs where there are just 50 different machines tracking things. So the more features we actually measure and track, the higher dimensionality of the space that we have. And if we don't have more data to occupy that space, our data becomes very sparse. And the more sparse the data is, the more difficult it is to model it. So increasing the dimensionality, increasing the number of things that we measure without increasing our data, the number of training samples, actually has a negative effect. And so this is a simple example of that, of where there's an optimal number of features that will give you the best performance, and increasing the features beyond that without increasing the data doesn't really help. All right, so that's kind of a whirlwind tour of some of the basic problems that exist, not only in machine learning, but in all scientific studies. These are really things that I think of as flaws in experimental design. And most of the problems that we've heard about in the last couple of days, failures of machine learning, can be attributed to something similar to that. But there's another issue. This is the one thing that I think nobody has really talked about, which is that machine learning, in spite of being 60 years old, is still relatively new and really just lacks some of the basic fundamental theoretical foundations that we see in other disciplines. Peter Norvig has said that we don't have appropriate processes for debugging and verifying machine learning systems. There are problems of with non-stationarity. This is something that kind of showed up in the failure of the Google Flu Trends, where it seemed to work very effectively for a while, but because of the changes in the Google search algorithm and change in user search behavior, failed spectacularly in the long haul. So my contribution to this, in the kind of the neat versus scruffy thing, is to, on the neat side, say that we need to put some effort into the foundations of what we're doing with machine learning. And strangely enough, a group that I would not have expected, DARPA, the Defense Advanced Research Project Administration, who brought us the internet, is actually doing something about this. And strangely, again, not really being noted for their sense of humor, they have this project called FunLol. FunLol stands for the Fundamental Limits of Learning, and in this project they're addressing some of these foundational questions that I think will help us a lot. So one would be the number of examples necessary for training to achieve a given accuracy performance. So when DeepMind considered 30 million different possibilities in their Go player, would 20 million have sufficed? How much better would they have done with 40 million? We don't have any theorems that really kind of give us a picture. So I did hear one of our presenters yesterday mention that we need a theorem about that, and I think that could help quite a bit. What are the actual effects of noise and error in the training data? Again, if we could have some way of quantifying these things more directly, I think it would help. Efficiency is something that computer science know about many algorithms, but not so much for machine learning algorithms. And I see I'm out of time. Machine learning has had some spectacular successes and spectacular failures, but we're right at the beginning of this. I think a lot of the problems that we've seen are just the result of poor experimental design. We're just getting started, and it's a great time to get on board and get on board the rocket ship. Thank you.
Well, thanks to all of you for those comments. One thing I noticed is that something that came up for every speaker, although we haven't named as yet, and so I'd like to put a name to it, is something that we'd call the multivariate nature of medical decision making, and this is something that machine learning is particularly good at. For those of you who don't know, multivariate refers to, well, think of it as this, it's the exact opposite of what we do when we look at a lab test, right? So when you look at a lab test, the way it at least it gets presented to the patient is a number of univariate tests. It's, is this test higher or lower than this threshold? And if it's higher than the threshold, we say it's too high, and if it's not, we say don't worry about it. Whereas a multivariate test would be something where everything is looked at holistically and together, and then a decision is made based on all of that together. One of the challenges for kind of a lack of any much kind of multivariate disciplines in medicine is that medicine is very much set up not to do this kind of thing. So for example, May mentioned this case where wealthy, educated white women were getting better results on a test, and that was incorrectly assumed to be associated with an intervention. And it wasn't actually because of the intervention, it was actually because of the fact that their social status. Another great example, I think, would be the people who are about to get a breathing tube. You know, it looked like the drug that they got ahead of time was something that was causing them to become sick, but actually it was something else that caused the doctor to think, let's give them the breathing tube. So there's, I wanted to ask you a question about that, John, before we get to these questions. I faced a very similar issue in a company I ran for 10 years, which was in insurance. And in insurance, we wanted to help insurance companies to set the right price. And the right price for an insurance company is the price that makes them the most money. And so that means one of the things they wanted to know is which customers would drop their insurance if you raised their prices and which ones wouldn't. And so we really wanted something just like your example that said, what would this intervention do? We wanted something that said, if you raise this price to this customer, what would be the probability of dropping insurance? And we had the same problem you had, which was that the insurance company had no prior history of knowing what happened when you increased prices to those customers, because by definition, those customers had that price. So we had to convince our clients to spend an opportunity cost of about $30 million to start actually randomly setting prices for a while, find out what happened, as a result of which we got the kind of data which we've just heard from Michael about, basically represents these kind of these areas that hadn't been seen before, so that we could extrapolate to those areas. So that turned out to work fine in insurance. We convinced them by running simulations that showed that the outcome upside would be about $250 million if they spent the $30 million downside. But I was wondering, in your case, have you thought about this question of knowing, you know, at what time should we do what intervention in situations where that hasn't been done yet? You know, the cost is not $30 million. The cost potentially of getting that piece of data might be killing somebody. You know, how do you deal with this issue of lack of data, particularly in these complex multivariate spaces? You know, what's the approach to experimental design in the world of machine learning as opposed to the world of kind of univariate t-tests?
Well, the way we think about it is, you know, there'll be situations in which there's uncertainty in what's the right thing to do. And there will have been already, effectively many experiments have already been done, right? With a large enough data set in situations where there isn't really necessarily a standard of care. A lot of different things have actually been tried in the past. And those are precisely the areas where we think we can help, where there's uncertainty. So hopefully in those areas, there's already some I guess, variety of experience that have been done from which you can learn. Lacking that, you know, yeah, there's nothing you can do. We don't know how to extrapolate beyond what's already been seen in the data set. But I suspect that those are the areas where maybe we don't really care about. That may be wrong, but hopefully the areas where the same thing is done all the time are the areas where the doctors maybe feel like there's a good standard that they're already following. I guess you can imagine limitations to that, right? You can't learn beyond what's already been done, and maybe there is something more optimal that could be done, but is not being done.
Yeah, I mean, it's interesting. It's not just in medicine. I've seen this. I've attended conferences in economics where they face exactly the same issue. In the world of economics, kind of social science, all of their experimental design in the past has been based on univariate tests, you know, ANOVA tables, stuff like that, and it's much harder to deal with noise in that situation because you end up with two groups who differ in ways you didn't realize, whereas with machine learning, particularly with the kind of things like recurrent neural networks you described, we can kind of deal with all of those at once. I wanted to come back to one of the questions that have been asked here. Dr. Suresh, what are the considerations for your hospital moving to a public encrypted cloud platform like Google for building your AI models and analytics? I think this is a really interesting question. As a CIO, I'm sure you've got some interesting perspectives. I've seen in my previous medical startup, the benefits of moving to the cloud can be huge, particularly if we're able to combine data sets together. We can potentially find more of these kind of gaps. We can build more powerful predictive models. at the same time, I saw a lot of pushback from hospital administrators for all kinds of regulatory and legal reasons. What are your experiences here? Because I think this really impacts machine learning a lot.
Sure, great question. We are certainly getting there, but slowly, really slowly. Most hospitals, probably the majority of them, our EMRs are hosted locally. We don't do remote hosting. That's based on privacy and security concerns. Some of those may be unfounded, but at least at Children's and UPMC, we have a new sepsis recognition tool. For that, we have to use mobility solutions which have to be in the cloud. So we said okay to it for the first time in our history. We'll have a remote hosted platform, and I'm talking about for EMR enhancements. Going to analytic platforms, we do this in limited ways. We collaborate with MedCPU, which is an Israeli-based company. We use Qlik advanced analytic dashboards. So we are totally not opposed to a cloud-based platform after doing our due diligence, realizing that some of the AI tools will give us much more timely and quick returns. So the short answer to it is we're certainly moving towards it, but the pace is going to be slow.
Thank you. This is a great question, and maybe, Michael, since you're our ELI 5 person, you can help with this. The question is, can you explain data leakage and how to mitigate this? The reason I wanted to highlight this one is because at KDD, which is one of the top machine learning conferences, as you know, a couple of years ago, the top paper was actually given to a group of people who discovered that this thing called data leakage occurs in more than half of machine learning projects. And anytime you have data leakage in a medical context, that could be life-threatening. So maybe you want to answer this question?
I'm going to have to pass on that one. I really don't have a good example or a good way of thinking about that.
Okay, no problem. I can help here. So as I mentioned yesterday, I used to be at this organization called Kaggle, which runs machine learning competitions. And the KDD paper actually got its data from machine learning competitions. So a great example of one we saw was a group came to Kaggle saying, can you have your data scientists look at this prostate cancer data set and come up with a machine learning model for this? And we very quickly found a machine learning model which had 99.99% accuracy at identifying prostate cancer, because it turned out one of the data elements in the data set they had given us was a Boolean variable, have they had prostate cancer surgery or not? So this is an example. A non-medical example I've seen was the University of Melbourne gave us a data set saying, can you predict which research grants are likely to be successful? And it turned out that the field for date submitted was nearly always null unless they ended up accepting the application, at which point they would go back and fill it in. So a non-null date submitted field had almost 100% correlation with successful grant applications. So the reason I wanted to highlight this is that data leakage is something which, even in very sophisticated machine learning organizations, happens more than half the time, and it breaks everything in terms of like your assessment of whether this model is going to work, because if it had data leakage, then you're going to be massively overconfident, and there's no statistical test of data leakage other than does this model look ridiculously successful and do the predictors in it seem to be inappropriate?
I can give an example of one thing that we look out for in terms of data leakage. So I think of data leakage as information from the answer seeping back into your training. And we, in the ICU, we split up our data cases into ICU episodes. And you have some patients can have multiple ICU episodes. And so it's important when you're training your data set, you're training your algorithm, you want to learn an algorithm that is going to perform well on a patient that's never seen before. So typically you do a cross-validation, but if you cross-validate at this episode level, you have some episodes from the same patient that are in the training set, some might wind up in the test set. Your algorithm has already kind of peaked at the test set by getting some of these episodes from patients that it's already trained on. So it's important when doing the cross-validation to make sure that the patients that you test on are patients that did not have any episodes at all in the training set.
Okay, so I probably want to answer the bias
Please.
question. So this is actually a very important question. That's also very common.
So I'll
in
just read the
machine
question
learning.
since it's off the
Yeah.
bottom. It says, how do you recommend to correct the anomaly when the output is biased due to biases in the input? As systems evolve, AI models will have to evolve with this.
So this is a very critical question because I'm the one that keeps saying that for biomedicine, AI, we have to do validation and have knowledge guidance, largely because the price we pay for wrong diagnosis is very high. It's a life and death situation. So as a result of it, when we actually induce the knowledge from the practitioner, we induce the bias, right, in the initial experiment design. Whatever you're doing, you already start inducing it. So that's why I'm providing two kind of strategies as engineer. I have been working on this field for a long time with a group of engineers, either from industry, also from academic, and also clinical, academic clinical centers. These are the two strategies when you're dealing with that. The first strategy we call robustness. When you actually develop a model, you actually have to embed this fundamental model robustness. Actually, today I couldn't show the cartoon, but in the workshop I did show that, where the basic concept is very simple. I use the airplane as an example. When we design an airplane, do we know every single possible turbulence up front? We do not know. But when we actually want the plane to stay in the air, we have to allow the margin, allow when the turbulence happen, the plane still stay in the air. That's what we call the embedded robustness in our model. So when you actually design machine learning model, your model parameters should not be absolute when you design any study. You should actually budget that robustness right there. That's allow when you actually, the data set start changing, you have the changing, you can deal with that. Number two strategy, very important. We call it, now there's a fancy name called LSTM, right? Long, short-term memory approach. The fundamental concept is really the delayed decision making. So you basically, anytime you make a decision on that point, especially real time, like decision making, you actually want to not only look at the immediately near term, the impact of what's happening when you develop your model, but also you want to learn the long back what's happening. This is actually for a lot of longitudinal studies, very important. Those are the two fundamental strategies we use to deal with the bias in the machine learning model.
And I think it's also one of the great challenges in terms of data availability. If you're going to use a recurrent neural network like an LSTM, you actually need that long time series that says these are all the things that were done to the patient and all the ways in which they responded over a long time period. And I haven't heard of many, if any, other situations other than the one you mentioned where you are, where that data set is being gathered and continually looked at by data scientists. I think it might just about be a unique situation. Is that kind of something that you guys are looking at doing, is trying to create this kind of big longitudinal holistic database?
Sorry, can't answer that. Don't know. Maybe a consideration for the future, but at this point, haven't thought along those lines. Can I make one point?
Please, sir.
So this is not answer to a question, but since I have the podium, I'm going to abuse my time and take a minute to put in a plug for pediatrics. We have heard so many great examples of AI and ML and deep learning over the last couple of days in adult cardiology, adult GI, adult radiology, etc. And looking at pediatrics as a whole, which I still feel is underserved from the latest technology explosion, there are 74 million kids in the US. That's 24% of the 24% of the country's population, 0 to 18 years. So that's your potential market size, so to speak, for any kind of large-scale data set analysis. Additionally, kids generally are well. They don't have a lot of comorbid conditions, so less confounders if you want to, again, analyze large, not just illness data, but also wellness data. And the impact when you look at unvaccinated kids or childhood obesity or mental illness in children is massive to the society. And somebody made this quote yesterday, it's easier to work on making stronger kids instead of repairing adult men or something like that. So to that effect. So just to keep that in mind, when you have a startup or other newer tools, to look at this 74 million cohort.
Great.
Thanks.
I'd like to thank all the panelists for introducing us both to the opportunities and the challenges of machine learning so effectively. Thanks.